Today I'll talk about chemical equilibrium. So here is the problem statement. For the reaction 2CH4 that is form C2H2 plus 3H2 at 151 degree centigrade, if Kc is 0.145 mole square L to the power 2 liter to the power minus 2, what is the relationship between Kp and Kc? Calculate Kp. Why is thermodynamic equilibrium constant unitless quantity? That we have to find out. Now here is the reaction. So 2 methane that is going to C2H2 plus 3H2. Now the equilibrium constant Kc is expressed in terms of concentration, and while Kp is expressed in terms of pressure. So Kc is concentration of C2H2 and H2 to the power 3 and divided by CH4 to the power 2. And then Kp is partial pressure of C2H2 and they multiplied with partial pressure of hydrogen to the power 3 because coefficient of hydrogen is 3, so stoichiometric coefficient, and then divided by partial pressure of methane to the power 2. Again here that stoichiometric coefficient of methane is 2. So now we are making a relationship. We are going to make the relationship. So for that we are considering that ideal gas law. So the ideal gas law relates pressure, volume, temperature and the number of moles. So PV is equal to nRT, we know that. So we can also write P is equal to N by V RT. So N by V is nothing but concentration, so P is nothing but CRT or concentration RT. So C is the concentration here. Now use the ideal gas law to relate concentration to partial pressure and also express partial pressure methane in terms of concentration. So partial pressure of methane is nothing but concentration of methane into RT. Similar way, so concentration of C2H2 is nothing but partial pressure of C2H2 nothing but concentration of C2H2 into RT. And also we can similar way express partial pressure of hydrogen in terms of concentration. So partial pressure of hydrogen is nothing but that is concentration of hydrogen RT. Now we know Kp and then we substitute all this partial pressure and then we will find Kc. So here Kp is nothing but partial pressure of C2H2 into a partial pressure hydrogen to the power 3, partial pressure of methane divided by partial pressure methane to the power 2. Now we have to put all this partial pressure and concentration relationship, then we will get the concentration and that RT whole square, means if we segregate concentration at RT. So we know that Kc is nothing but concentration of C2H2 and hydrogen to the power 3 divided by CH4 to the power 2. So that is nothing but Kc. So we can write that Kc into RT to the power square. So now ultimately we will get Kp is nothing but Kc RT to the power delta N. So here delta N is nothing but change in number of moles of gases between products and reactant. So here delta N is nothing but 2. So Kc R to the power square. So Kp is the equilibrium constant in terms of partial pressure, Kc is the equilibrium constant in terms of concentration, R is the ideal gas constant, so that is 0.0821 liter atm Kelvin to the power minus 1 mole to the power minus 1, and T is the temperature in Kelvin, and del N already I talked about, that is change in number of moles of gases between the products and the reactant. So here del N is 2. Now in that problem the Kc is given, that is 0.145 mole square liter to the power minus 2 for the reaction, or that is given that 2CH4 that is going to produce C2H2 plus 3H2, and assuming the reaction is at 1518 degree centigrade, not assume, already that is given. So and we need to determine, already we did that, so del N is that is 2. So now if we substitute everything, so Kp if we substitute here, so Kp is equal to, you know that Kp is equal to Kc to RT to the power 2. So if we substitute, so Kc is nothing but 0.145 mole square liter minus 2, and RT is 0.0821 liter atm Kelvin to the power minus 1 mole to the power minus 1 into that degree centigrade to Kelvin. So 1518 plus 273 Kelvin whole square. So we will get Kp is nothing but 3135.5 atm square. So now we get the relationship between Kp and Kc, and then now finally we got the numerical value of Kp. So final result, the relationship between Kp and Kc for the reaction, so that we got that, and Kp numerically we get that 3135.5 atm. So that we got that. Now next is the why is the thermodynamics equilibrium constant K unitless quantity. The equilibrium constant is dimensionless because concentration or pressure in the equilibrium expression are expressed as the ratio of relative to a reference concentration. The thermodynamic equilibrium constant K unitless quantity. So we can write Kp something like that K. It is not Kp, K. So that is partial pressure of C2H2 by that standard reference pressure, pH2 by standard reference pressure to the power 3, PCH4 by P star, that is to the power 2. Now it is nothing but the ratio. Okay, so all the ratio are actually unitless. So we can say that thermodynamic equilibrium constant K is actually unitless quantity. So here remember, this is not a Kp, it is a K. Okay, so that's it. Thank you.